Hi, my name is Percy Mistry. I'm a research scientist at the Stanford Cognitive and Systems Neuroscience Lab, and this work has been done along with Dr. Vinod Menon. So in this project, what we've looked at is elementary school kids who are solving simple arithmetic problems such as single or double-digit addition. Very often, the objective in such tasks is to understand brain regions or networks that play a role in the development of mathematical capabilities, especially when we are looking at children who might have mathematical learning difficulties or when we are trying to measure the impact of cognitive training programs. And typically, these tasks are measured in terms of the accuracy levels or the speed of completion along with other independent assays. Some of the key limitations of this approach are that children often use a mixture of different strategies, and during such a critical developmental stage, there are multiple neurocognitive processes such as executive control, strategy selection, variances in the efficiency of execution, performance monitoring, sequential effects, and even post-error learning. And if we are unable to capture all of these wide-ranging measures of individual differences, this can lead to a lot of confounding of the final behavioral patterns observed. If we are able to capture all of these latent measures and get a rich multidimensional picture of the individual differences, we can look at brain activity with a much higher functional resolution. We can make more meaningful diagnosis with respect to mathematical learning difficulties, and we can identify the precise aspects that cognitive training programs might help influence. That's exactly what we attempt to do in this project. We develop and implement a novel computational model of math cognition within a hierarchical Bayesian framework. This model incorporates elements of drift diffusion modeling, item response theory, augmented process models, and other mixture modeling strategies. And what we'll show along the next few slides is that we are able to validate the inferences made by these models in a very robust manner. So first, we look at how well this model can infer the latent use of retrieval strategies. Even an unsupervised version of the model can provide as good a classification of externally assessed retrieval strategies as supervised versions that rely purely on reaction time-based classification. We show that our supervised versions of our model actually significantly outperform the supervised reaction time-based models. And what we also find is that our model is able to infer item-level characteristics that explain item-level differences, including the problem size effect, as well as differences that go beyond the problem size effect, and that the model can predict very, very strongly external classifications such as the Wheeler index of item difficulty. Next, we show that the model parameters predict independent assessments of strategy use better than external measures of mathematical capability. We identify the pathways via which math anxiety and attitude to mathematics may affect behavior, namely by affecting the efficiency of retrieval and the switching time, which is the time at which a probabilistic decision is made on whether to switch from an autonomous retrieval-based response to an alternate strategy. Interestingly, the retrieval efficiency, the switching time, and the sensitivity of switching time also contribute to the longitudinal prediction of externally assessed math capabilities. Note that these contribute to improving the longitudinal prediction after accounting for the time and assessment on the same scales. Next, we look at a canonical correlation analysis, which shows that some of the model parameters are closely related to traditional measurements of domain-specific or domain-general capabilities, such as number operations or IQ. But that there are also some very significant cognitive parameters that affect mathematical cognition, but are not explained via any traditional measurements, but are captured well in this model. The model identifies a wide range of individual differences in the optimality of strategy selection, that is, how well children select when to use retrieval relative to their efficiency or efficacy of retrieval across items of different difficulties. Once again, the switching time, which also longitudinally predicted math reasoning capabilities, seems to be strongly correlated to the calibration of optimality. Finally, we use the model parameters to cluster children into distinct clusters showing distinct behavioral and cognitive process profiles, but also distinct patterns of activation in the medial temporal lobe and right hippocampal regions, which have in previous studies been implicated in memory retrieval during arithmetic. To conclude, we've implemented a novel cognitive modeling approach here, which allows superior inference about the neural and cognitive processes underlying mental arithmetic, provides a novel approach that can be used in similar domains and can be effective in both diagnosis and curating customized training and developmental needs by identifying multidimensional individual differences. Thank you for your time.